wonder about the forces expected to accomplish terrific movement. For example, that of a dolphin leaping out of the water, or the post vaulter, or the trip of a winged animal, or the circle of a satellite.
Last discussion, the study of motion is kinematics. But kinematics only describes the way objects move, their velocity, and their acceleration. Dynamics considers the forces that affect the motion of moving objects and systems.
Newton's law of motion, or the foundation of dynamics. These laws give a case of the broadness and effortlessness of standards under which nature functions. They are likewise all-inclusive laws in that they apply to comparable circumstances on Earth just as in space.
Experience suggests that an object at rest will remain at rest if left alone, and that an object in motion tends to slow down and stop unless some effort is made to keep it moving. Newton's first law of motion states that a body at rest remains at rest, or if in motion, remains in motion at a constant velocity unless acted on by a net external force.
The property of a body to remain at rest or to remain in motion with constant velocity is called inertia. Newton's first law of motion is called the law of inertia. As we know from the experience, some objects have more inertia than others. It is obviously more difficult to change the motion of a large boulder than that of a basketball. The inertia of an object is measured by its mass. Roughly speaking, mass is a measure of the amount of stuff or matter in something.
Newton's second law of motion is closely related to Newton's first law of motion. It mathematically states the cause and effect relationship between force and changes in motion. Newton's second law of motion is more quantitative and is used extensively to calculate what happens in situations involving a force.
The acceleration of a system is directly proportional to and in the same direction as the net external force acting on the system, and inversely proportional to its mass. In equation form, Newton's second law of motion is A is equal to F sub net over m. When only the magnitude of force and acceleration are considered, this equation is simply F net is equal to Fa.
Newton's third law of motion states that whenever one body exerts a force on a second body, the first body experiences a force that is equal in magnitude and opposite in direction to the force that it exerts. This law represents a certain symmetry in nature. Forces always occur in pairs, and one body cannot exert a force on another without experiencing a force itself. We sometimes refer to this law loosely as action-reaction, where the force exerted is the action, and the force experienced consequently the reaction. Newton's third law has a practical uses in analyzing the origin of force and understanding which forces are external to a system.
Free body diagrams or diagrams used to show the relative magnitude and direction of all forces acting upon an object in a given situation. The size of the arrow in a free body diagram reflects the magnitude of the force. The direction of the arrow shows the direction that the force is acting. Each force arrow in the diagram is labeled to indicate the exact type of force. The free body diagram depicts four forces acting upon the object. Objects do not necessarily always have four forces acting upon them. There will be cases in which the number of forces depicted by a free body diagram will be 1, 2, or 3. Let us now proceed with types of contact forces. Forces are given many names, such as push, pull, thrust, lift, weight, friction, and tension. Traditionally, forces have been grouped into several categories and given names relating to their source, how they are transmitted, or their effects. The most important of these categories are discussed in this section, together with some interesting applications.
Weight, also called force of gravity, or in symbols we have F sub g, is a pervasive force that always acts and must be counteracted We notice that you must support the weight of a heavy object by pushing up on it when you hold a stationary object, as illustrated in the figure. But how do inanimate objects like table support the weight of a mass placed on them? When the bag of dog food is placed on the table sags slightly under the load. This would be noticeable if the load were placed on a card table, but even rigid objects deform when a force is applied to them. Unless the object is deformed beyond its limit, it will be exert a restoring force much like a deformed spring, or trampoline, or diving board.
We must conclude that whatever supports a load, be it animate or not, must apply an upward force equal to the weight of the load, as we assumed in view of the previous examples. If the force supporting a load is perpendicular to the surface of contact between the load and its support, this force is defined to be a normal force, and here is given by the symbol F sub n. The word normal means perpendicular to a surface. The normal force can be less than the object's weight if the object is on an incline.
A tension is a force along the length of a medium, especially a force carried by a flexible medium such as a rope or cable. The word tension comes from the Latin word meaning to stretch. Not coincidentally, the flexible force that carry muscle forces to other parts of the body are called tendons. Any flexible connectors such as a string, rope, chain, wire, or cable can exert pulls only parallel to its length. Thus, a force carried by a flexible connector is a tension with direction parallel to the connector. Another example of tension is a massive stone that is being pulled by a man across a frictionless floor by a rope at an angle theta. The tension in the rope causes the stone to slide across the floor to the right with an acceleration A as shown in the figure.
Friction refers to a force that precedes motion between materials in contact. When a force is applied to a body resting on a rough plane so that the body moves or tends to move, a frictional force acts on the body in opposition to the applied force. Friction exists in all types of materials. Friction between solid surfaces is generally classified as static, kinetic, and rolling, while in fluid, as termed for liquid and gas, as fluid friction or drag force.
Static friction and its symbol is F sub s. Static friction occurs in cases where friction to prevent relative motion between the surfaces. Examples of static friction are letter A, a car parked on a field. The brakes apply static friction to the wheel hubs and the wheels hold fast to the ground because of static friction. Letter B, a rock climber climbing a chimney, which is a gap between two stone walls with no handholds or grips but plenty of friction.
We have kinetic friction or F sub k. Kinetic or sliding friction is the friction present when there is relative motion between the surfaces in contact. Examples of kinetic friction are the tube on a lotion bottle and the opening to the lotion when it is pushed down to let out lotion, and jeans on your legs when putting them on.
Rolling friction. It occurs when one surface rotates as it moves over another without sliding or slipping at the point or area of contact. Examples of rolling friction are letter A, a skateboard set on a slide and glide will eventually stop itself because of the resistance caused by the friction between the wheels and the surface. Letter B, bike wheels that are thicker will lessen the potential speed of the bike because there is a greater wheel surface to create friction against the surface, which will slow the bike.
Next, we have the fluid or drag force. Fluid friction or drag force refers to the forces that resist relative motion of an object through a fluid or of a fluid through another fluid. Examples of fluid friction are when an object is dropped into a fluid, the extent of splash due to the buoyant force of the fluid depends on the fluid friction of that particular fluid, and air resistance caused by the particles that make up in air.
Now, let's talk about the laws of friction. The following are the laws governing sliding, kinetic, and static friction. Number one, static friction is greater in magnitude than in kinetic friction. Well, experience tells us that we need to exert greater force to start than to maintain motion. Number two, friction acts parallel to the surface in contact and in a direction so as to opposite motion. Friction cannot produce motion. Its main role is to oppose motion. Number three, friction is independent of the area of contact and speed of sliding. Number four, friction is proportional to the normal force. Number five, friction depends on the nature of surface in contact and condition of surfaces. That is whether the surfaces are rough, smooth, polished, or wet.
Thank you very much for watching.
We hope that you learned.
See you on our next topic. Bye!